Hello everybody, so we are back for chapter 6, lecture 3, and we're going to be talking about ATP and energy coupling. So remember, coupling just means linking together. So last video we talked about the fact that in cells there can be endergonic reactions and there are exergonic reactions. Endergonic reactions require an input of energy in order to move reactants uphill to products that are at a higher energy, whereas exergonic reactions release energy to the surroundings. Okay, but the main idea right now is just to remember that coupled reactions are linked together. In other words, you cannot have an endergonic reaction without linking it to an exergonic reaction. The exergonic reaction is going to provide the energy that is necessary for the endergonic reaction to happen. So, endergonic and exergonic reactions must be coupled. They must be linked together. Now, it's important to think about how much energy is required. So if we have an endergonic reaction that requires this much activation energy to get the reaction to go, then we cannot couple that reaction to an exergonic reaction that has a very small delta G. Because this delta G, the amount of energy that's released into the surroundings, is not enough to get over the activation energy barrier for that endergonic reaction. So the delta G for the exergonic reaction has to be much greater than the activation energy required for the endergonic reaction. Because remember, no transfer of energy is 100% efficient. So there's going to be energy lost. So in order to get our endergonic reaction to go, we're going to have an exergonic reaction that has a much bigger delta G. Okay? Well, cells will oftentimes use ATP as the source of cellular energy. So ATP stands for adenosine triphosphate. So notice this looks very similar to a nucleotide. That it's the ribose nucleotide. So this is very similar to the A that is in RNA. The main difference is that this is the triphosphate version. So there are 3 phosphate polyatomic ions attached to the sugar instead of just one phosphate group on that 5' carbon. All right, so why is ATP a source of energy? Well, it's because of all of the energy that is stored in the bonds that are holding those negative phosphate groups to each other. So you know that like charges repel. So if you've got 2 negative phosphate groups, those are naturally going to repel each other, kind of like when you have two magnets with the same poles facing toward each other. You can feel them pushing at each other. Well, negatively charged groups are the same way, but that repulsion can be overcome, and those two negatively charged groups can be covalently bound together. Well, some of the energy that was required to link those two phosphate groups together is now stored in that chemical bond. But when you get ready to put a third negatively charged phosphate group on, it's going to take even more energy because the negative atmosphere is more than it was when we hooked the first two phosphates together. So there's even more energy stored in that bond. Okay, so because of the energy that's stored in those bonds, ATP is a source of molecular energy. ATP is a relatively unstable molecule because of these natural repulsive forces of the negative phosphate groups. Cells cannot stockpile ATP. That's why cells are going to store excess energy as fats and polysaccharides because they're more stable. Even though those fats and polysaccharides can be converted into ATP when the cell needs energy, it can't just stockpile that ATP. All right, so when it is time for a cell to use energy in ATP, ATP is going to be hydrolyzed, which means an enzyme is going to come in and it's going to break the bond between the second and third phosphate group. And when it does that, energy is released. Okay? Well, because that energy is released, this is an exergonic reaction. Okay? So our reactant was ATP. Our product is ADP plus that inorganic phosphate group that was cut off. And then that energy that is released can be coupled or linked to an endergonic reaction. All right, so for example, in order to take glutamic acid, which is an amino acid, plus ammonia to make glutamine, which is another amino acid, there's a delta G of a positive 3.4. That positive 3.4 tells us that the reaction is an endergonic reaction, okay, which means we're going to have an input of energy to get that reaction to happen, okay? Well, the cell is going to couple, let's just kind of skip panel 2. The cell is going to couple the hydrolysis of ATP and the release of its energy. Notice it releases negative 7.3 kilocalories per mole, whereas our endergonic reaction only requires a positive 3.4. Okay, so that negative 7.3 kilocalories per mole is going to be linked to this reaction that is synthesizing glutamine. Okay, so if we wanted to visualize that with our energy progress curves, here we have our hydrolysis of ATP linked to our synthesis of glutamine. Notice that our activation energy that's required for our endergonic reaction is less than the free energy change for our delta G, for our ATP hydrolysis. Okay, so Cells can couple ATP hydrolysis to a variety of reactions as long as the necessary energy is less, significantly less, than the amount of energy released from ATP hydrolysis. Okay, well, so everybody always asks, well, then what does the cell do with that phosphate group that's released when ATP is hydrolyzed? So the cell can take ADP, which is adenosine diphosphate. That's what's left after that third phosphate group is chopped off. So di means two, so adenosine diphosphate. The cell can take that phosphate group in ADP and reform ATP. But the formation or the synthesis of ATP is a highly endergonic reaction. Okay? ATP synthesis only happens during certain reactions of metabolism, and that's going to be the subject of chapter 7. Okay? But it doesn't just happen, you know, an ADP and a phosphate don't just bump into each other in the cytoplasm and automatically join to make ATP. Okay? It requires an input of energy to do that. And then when ATP is hydrolyzed, that energy is released for the cell to couple it to other processes. Well, so where does the energy to build ATP come from? Well, it's mainly going to come from other catabolic reactions, primarily breaking down glucose and using the energy in glucose to build ATP. And again, that's going to be the subject of chapter 7, all about aerobic respiration.